So a very, very long time before anyone considered light as a wave, it was purely considered to be a bunch of small particles because people were able to observe particles pretty easily back then, as everything is a particle. So they assumed that light followed all the same rules that everything else did. So we're going to start talking first about classical optics. And classical optics just refers to everything that was known before light started being considered a wave. So in Newton's time, light was studied as if it was purely, just had particle properties. Um, so one thing is that it moves in a straight line. Moves in a straight line. It bounces or rebounds off objects that it bumps into. And last one, it passes through objects that offer minimal resistance. Where, you know, this model just is not good enough to explain some things that we'll see happen. Um, but for where we're going to start, it's perfectly adequate for dealing with a lot of everyday things that we see, and it'll help us, knowing these things will help us start talking about mirrors and lenses. So one of the first topics in classical optics we'll get to is all about reflection. So when you hear the word, no, when you hear the word reflection, you probably think of a mirror. It's not going to let me add it because I'm too far down the page. Alright, let's get this squared away here. Alright, so you hear reflection, you probably think of a mirror. But everything that we see is able to reflect light. If an object couldn't reflect light, we wouldn't be able to see it at all. The only reason that we know things exist is because they reflect light, which bounces onto our retina, onto the back of our eye, uh, and gets changed into an electrical impulse that is sent to our brain. So, mirrors are kind of a special case, though. Most objects in everyday life absorb some light and only reflect some of it back. Only certain frequencies get reflected back. And that, kind of defines why some things are certain colors. um, Most objects also have a rough surface. If you get really, really far down on the, microscopic level, even a sheet of paper is pretty rough. So light gets reflected in all different directions. The rough surface bounces it in all kinds of different ways. Mirrors, though, are so smooth that they're able to reflect all the light that strikes them in what turns out to be a very predictable way. So we need to get some terminology here before we move on any farther. So since we're talking about light kind of in the particle um, mindset, we're going to treat it like rays. A ray of light is just a line. It moves in one straight direction until it runs into something. So we'll call a ray of light that strikes some reflective surface an incident ray. Or we could say that the ray is incident on whatever object. ray comes in, hits some object, and the ray that bounces back is going to be the reflected ray. That's the one that bounces off, or hey, gets reflected. Alright, we'll define two different angles here in these models. The first one being the angle of incidence. That will just be a plain old theta. You might see theta 1, theta I. You might see it all different ways, but as long as you know what it's about, you'll be able to figure out what to do with all the rest. And this angle of incidence is going to be the angle that exists between the normal, so the line that points straight out of the mirror, a line perpendicular to the reflective surface, and the incident ray. So similarly, we have the angle of reflection. This one is theta prime. You might see theta f, theta r, theta 2. Again, it doesn't matter as long as you know what it's doing, you'll be fine. So the angle of reflection, that's the angle between the normal and the reflected ray. So here's a little diagram of all our different things. We have our incident ray coming in from some incident light source. It comes straight in, hits this totally reflective surface, and you can see here how the normal points straight out from the surface. It makes a 90-degree angle with your reflective surface. So your angle of incidence exists between the normal and the incident ray. Your angle of reflection exists between the reflected reflective ray and the normal. Alright, so we have a handy little law here, the law of reflection. And what the law of reflection tells us about the angle of incidence and angle of reflection is that they have to be equal. So theta, the angle of incidence we just call plain old theta, is equal to the angle of reflection, which we call theta prime. Again, you might see theta 1, theta 2, all the different names all mean the same thing. So the reflection of a ray light works just the same as a ball bouncing off a wall, except gravity, as far as classical optics is concerned, has no noticeable effect on these light rays. We'll get into cases later on, and we had a question asked when we were going over our waves review about gravitational lensing, which obviously means that light is affected by gravity. But for this simple old-timey case that's going to set up the backbone of everything that we talk about, we don't really have to worry about that for now. To reflecting light, a lot of surfaces are also able to refract light. So refraction just means rather than bouncing off the surface, some of the incident ray is actually able to travel, that doesn't say through, travel through the surface. But it happens at a new angle. So some of the light passes through, but it changes the angle. So we're able to see through things like glass through water because a lot of the light that strikes those substances gets refracted and passes right through them. So when you have light passing from one try it again. Light passing from one substance into another will almost always at least partially reflects. So not all of it is able to make it through. Some of it gets stuck behind and gets reflected. So you still have an incident ray, you still have a reflected ray, and they both have the same angle to the normal. So your angle of incidence and reflected angle, or angle of reflection, have the same angle to the normal. But then you also have a third ray, which is the refracted ray. So the refracted ray lies in the same plane as those two rays. The only thing that we can say about the angle of the refracted ray, though, is that it will not be the same as the angle of incidence nor the angle of reflection. At objects that we see from one medium to another, such as a straw in a glass of water, um, actually appears distorted. It's either bent in shape or, kind of broken, as it sometimes seems, because the light bends when it passes from one medium into another medium. So in this diagram we have medium 1, and it has some characteristic called index of refraction n1. We have medium 2 with its own index of refraction n2. So these indices of refraction are just kind of characteristics of two different mediums. They really have no meaning on their own. Um, the only time they're important is when you put them together. So it's kind of like a ratio of just how much your light is going to get bent when it passes from one to the other. So here again we have our incident light coming in. There's your angle of incidence. The reflected light is definitely pointing the wrong direction. It should come in, incidence, bounce off, and get reflected. So that arrow definitely needs to change. And then you can see a little bit of the light has passed right through from one medium to the other and got refracted at a different angle. This one happens to be smaller than the incident and reflection angles. Alright, so the phenomenon of refraction is actually a result of light traveling at different speeds in different media. So light travels a little bit differently through water than it does through a vacuum. It travels differently through air than it would through glass. Um, so all those different speeds cause um, this light to get refracted in these ways. So the speed of light constant, the c we talked about earlier, is really the speed of light when it's in a vacuum. So when light passes through matter, it's actually slowing down. If light traveled through some substance with this velocity v, then that substance has an index of refraction of whatever its speed is divided by the speed of light. Whoa. So variable that you're going to see for index of refraction is lowercase n. So because light always travels slower through matter than it does through a vacuum, oh, I actually put this in the wrong order here. N is should be c divided by v. So because light always travels slower through matter than it does through a vacuum, then v will always be less than c, which means that n will always be greater than or equal to 1. Yeah, this is where I caught myself. When the way I had it set up before, n would have always been less than or equal to 1, and that wasn't working out for me. Alright, so for transparent materials, typical values you might see for n are really quite low. So, you have the index of refraction for air, that's 1. Um, so light is able to move at pretty much the speed of light through plain old air. Water gets a little bit slower, glass even a little bit slower, and because it's the presence of matter that's slowing down the light, denser materials generally have really high indices of refraction. So denser materials generally have much higher indices of refraction. Alright, so how do these um, indices of refraction actually affect light? When you have a light ray that passes from a less dense medium into a denser medium, it's going to get refracted toward the normal. So remember, the normal is the line that points straight out from the reflective surface. Um, so if you go, say, from air to water, the light gets bent toward the normal. And a light ray that passes from denser to less dense will do the opposite. It'll get refracted away from the normal. So for example, water is denser than air, so when you have light travels out of water toward your eyes, it gets refracted away from the normal. If you look at a straw in a glass of water, um, you see the straw where it quote unquote would be if the light was traveling in a straight line. Your brain isn't able to tell that, hey, this light is changing mediums. No, it sees things in straight lines. So if you have a setup like this where that's you, your little eyeball, and you're observing this straw in a glass of water, then what you're seeing here um, is oh, alright, the straw. Oh my goodness, what is going on? There is a light wave that gets reflected from the tip of the straw, and it moves up towards the top of the water. We can make it lean more a little closer towards your eye. So it's kind of like heading in that direction. Alright, so once it hits the surface where the air and the water meet, it gets refracted. Since it's going from more dense to less dense, then if we say this is our normal, the line that comes straight out of the surface of the water, then the ray is going to bend away from the normal here and move off to strike your eye. Alright, so recap so far. Light gets reflected off the bottom of the straw, hits the surface of the water, gets refracted away from the normal here. So since your eye isn't able to tell, oh hey, something changed medium, it got bent, what it's actually seeing is that, oh my gosh, what it's actually seeing is something like this. It thinks things happen in straight lines. So it thinks that you're actually seeing some kind of straw thing that is way out here in the water, when in reality it's actually down here. So if we're given a ray traveling from a medium with an index of refraction n1 into a medium with index of refraction n2, then we have a relationship called, no, Snell's law. And Snell's law governs the relationship between the angle of incidence and angle of refraction. So what it says, it's really, really simple. N1, so index of refraction 1, multiplied by sine theta 1, so the angle that it comes in at, or angle of incidence, I guess I could use the right name, will be equal to index of refraction of medium 2 multiplied by sine of angle of refraction. So n1 sine theta 1 equals n2 sine theta 2. So example here, we have a ray of light passing from a liquid medium into a gas medium. The incident ray has an angle of 30 degrees with the normal, and the refracted ray has an angle of 60 degrees with the normal. If light travels through the gas at a speed of 2.5 times 10 to the 8 meters per second, what is the speed of light through the liquid medium? Wow. All right. So if we went through here, we could see that we have theta 1 and theta 2. We know nothing about n1, nothing about n2. We have speed through the gas. We want to know what is speed. So this is our goal, to find v uh, liquid, I guess. Speed of light through the liquid. Alright, so to do that we're going to need some help from Snell's law. So n1 sine theta 1 is equal to n, whoops, I did that backwards. N2 sine theta 2. So theta 1 and theta 2, awesome, we're given that. Alright, do you remember the relationship between v and n if we wanted to replace n with um, something to do with v? Remember, it's c divided by v, and I'm still in subscripts. Alright, so let's make those substitutions. So for n1, we'll have c divided by, let's see, okay, I guess 1 we're calling the liquid side, so we'll leave that v liquid. Alright, and sine theta 1. Alright, that's going to be equal to c divided by speed of light through the gas multiplied by sine theta 2. Alright, so here's our V liquid. Here's what we want to find. C is a constant. We always have that. We were given theta 1. C pops up again. We have V gas. And we have theta 2. So it's just a matter of rearranging from here. Alright, so I multiply V liquid up here. Divide by the rest of this stuff over here. And we'll have C. Well, since we have a C on both sides, we don't even have to worry about it. They would cancel each other out. So what we wind up with is that V liquid is equal to V, well, equal to sine theta 1 divided by theta 2, sorry. This would be so much easier if I could just write it out. Alright, so sine theta 1 gets divided over here, so it's in the denominator with V gas because we canceled out the C's. So V gas sine theta 1. Alright, so plug in some values. Theta 2, we were told, is 60 degrees. So V liquid equals sine 60 divided by 2.5 times 10 to the 8th, multiplied by oh man, that'll get us the inverse. Alright, so that's going to be 1 over. So we just have to invert that. I just did my algebra a little bit backwards. I left V liquid over here. I knew I put sine theta 1 on the top for a reason. Yep. Alright, so we're going to want to invert this when we're done. Your equations, when you do the algebra the right way, will not look so complicated, so don't be intimidated by this. So, let's see what we get here. We'll have that V liquid is equal to 1.45 times 10 to the 8th meters per second. It's not uncommon to see things in terms of the speed of light. So when you start, or speed of light in a vacuum, it's all the speed of light that we're talking about. So in this case, we have 1.45 times 10. Oh no, that's not what I wanted. All right, 1, 2 divided by Alright, so this is about 0.48 C, might be another way that you could run into seeing this. So 0.48 C, so about half the speed of light in a vacuum.